As we have seen in previous videos, we know how to notate our neurons, weights, and we know also what every function here do. But now we'll understand how the error work. That is the finally function. Because when we have the input data, we calculate with the function f the net of the neurons of the next layer, and also with the bias and every wave. Then we will activate each of these neurons with the activation function and calculate the output the out neurons of this layer. Then we will apply another time the function f, but here I call it g, and we'll calculate the net of the output layer, that is here. And then we will apply another time the activation function and calculate the final output values that are the predictions of the network. But here we have three layers. What happens if we have more than three layers? So as you have seen, we'll have the function f between two different layers, okay? And also for each layer that is not the input layer, we will have an activation function, okay? Like here. So because we have three layers, we'll have two functions that are f. But if we have four layers, imagine that we have here a, a, a neural network that has four layers. So here we have the connections, okay? I don't write the states of the neuron because here we have the net and the out for every neuron, okay? So here we'll have a function f here, then activate these neurons, then another time a function here f, that we will call it g in this case, here f, and here h, because we'll have another function here, and here the activation function, okay? And finally here we will have another activation function, okay? So it will be the same when we do the neural network in Java. We'll apply this, okay? So with this we know the simple notation, but when we do the Java program, we will be structuring and ordering the data because it's very important. So as you know, we have a wave, we have a bias, and also we have a neuron value. If the neuron is activated, it will have this notation. If the neuron is not activated, it will have this notation. For simplicity, the out value, that is the real value of the neuron, will be notated as the xi, okay? So now that we know this, we can do this in a matrix form, okay? So we'll define the vector x of neurons as a vector, okay, that will have all the neurons, okay, and finally we'll have, if the length of the neurons is n, it will have this form. For the bias, the same as the neurons, okay, we'll have, sorry, it will be uppercase, and we'll have this bias and a final bias that it will be a size of, sorry, n. Now also we can define the weights in a matrix, okay, that we will notate it as the weights in position L. As you should know, here this layer will be associated to layer 1, so the weights here will be in layer 1, the weights here in layer 2, and here in layer 3. Okay, so if we have this size of this layer n and the size of this layer m, we can denote the weights as a matrix where we have the weight in position 1 1 of layer L, the position 1 2 1 in position L, and to position N1 in position L. Okay, the same here. That will be here 1 2 1 1, sorry. Yes, 1 2 2 2 and N dot 2. And finally we'll have here dot M 2 dot M, and here NM. Okay, so this will be the notation of a matrix of the weights. As you can see here, this row, for example, will be all of these weights. Okay, the second will be the destination will be the name 1 2, so it will be here, so all of these weights.